We'll be looking at the activation functions and their role as applied in the neural networks. So what is an activation function? An activation function, also referred to as a transfer function, is a nonlinear function applied to a neuron to introduce nonlinear properties in the network. It manipulates the presented data and produces an output for the neural network that contains the parameters in the data. Note that a relationship is said to be linear if a change in the first variable corresponds to a constant change in the second variable. And a relationship is nonlinear, meaning that a change in the first variable doesn't necessarily correspond to the constant change in the second. However, they may impact each other, but it appears to be unpredictable. The activation functions can be basically divided into three types. One is a binary step activation function. You have linear activation function, nonlinear activation function, and we shall look at each of the activation functions in the next slides. So binary step activation function, we say that it's the simplest threshold-based activation function, which works by either activating the node that is passing on its output to the next layer in case the threshold value is surpassed, or doing nothing at all. The output for this activation function is binary, taking a value of 0 or 1 based on whether the input is below or above a certain threshold. It was used historically, but not common in modern neural networks due to non-differentiability, which poses challenges for gradient-based optimization algorithms like back propagation. So these binary step activation functions was used historically, but nowadays, because neural networks they are continuing to be more complex. So, and you see, just relies on binary output that is 0 or 1. So it's not much nowadays. Therefore, it is generally not suggested to use binary step activation function in the hidden layer, as it is a linear piecewise function, which is unable to handle complex presentation or representations. So this one is not able to handle complex representations. That's why it's not very commonly used nowadays. Another activation function is a linear activation function. And the linear activation function, also known as identity, multiplied by 1, simply returns the input as the output. So there's that mapping of 1 to 1. Okay? That is, the output is directly proportional to the input. The linear activation function does not change the weighted sum of the input in any way, and instead returns the values directly. It is often used as the activation function in the output layer of a regression problem, where a direct prediction is required. So it's usually used in the output layer of a regression problem. However, it's rarely used in hidden layers because stacking linear functions results in another linear function, which limits the model expressive power. So it is used in the output layer but rarely used in the hidden layers because of the linear property, which limits the model's expressive power. Look at the third activation functions is nonlinear activation function. Nonlinear activation function introduces nonlinearity to the network, allowing it to learn complex relationships in the data. Some nonlinear activation functions include sigmoid function, hyperbolic tangent function, rectified linear unit function. We say that these ones are widely used in hidden layers to enable the network to learn and approximate nonlinear mappings. These functions facilitate the learning of intricate pattern and representation in the data. So this one allows to learn complex problems and now that means it's now currently very much used because of that capability to handle complex situations. So nonlinear activation functions are essential for the success of neural networks in approximating complex functions and capturing nonlinear relationships in the data. So I would add and say that the sigmoid function, as I stated, that there are some linear activation functions include sigmoid function, hyperbolic tangent, and the rectified linear unit. We see that the sigmoid function curve looks like a S shape, and it's especially used for models where we have to predict the probability as an output. The range of the tangent, remember we said that we have hyperbolic tangent functions, that is part of the nonlinear function, and we said that the range of the hyperbolic tangent function is from -1 to 1 and is mainly used in classification between two classes. However, the rectified linear unit is the most used activation functions in the world right now because it is used in almost all the convolutional neural networks or deep learning. So we find that rectified linear unit is the most commonly used nonlinear activation function in the world right now because it can handle much of the complexity and now very useful in deep learning. And you look at the convolutional networks data, you see how they are and why this rectified linear unit is very much important. So those are the three types of nonlinear activation functions. So in the conclusion is that the choice of activation functions that one chooses for a neural network is crucial. It's a crucial decision that can impact the performance of the model. So remember, the activation function that you settle on will determine how the model will perform. Like if you choose for a sigmoid, that is, if you pick a nonlinear activation function, another one picks a linear, yeah, there will be some different. And you are able to see now some are able to handle complex situations, others are not able to. Different activation functions serve different purposes, and the choice often depends on the specific characteristic of the problem you are trying to solve. So ensure that you understand the problem well, and it's from understanding the problem now you can be able to settle on the activation function to use. If your problem is quite complex or you have some many hidden layers, then you have to settle for a nonlinear activation function like the rectified linear unit. To learn more about each type of the activation functions, use the textbook that you can easily find in the library by Art John and Richard G. Palmer. That is called Introduction to the Theory of Neural Computation. So yeah, if you reference that material, you'll get more input on those types of activation functions and you'll be able to understand more.